Newton's rings. Newton's rings are visible when a planar convex lens is placed on a flat glass surface. For a particular lens with an index of refraction of n equals 1.5 and a glass plate with an index of n equals 1.8, the diameter of the third bright ring is d3 equals 0.64 millimeters. If water n equals 133 now fills the space between the lens and the glass plate, what is the new diameter of this ring? Assume the radius of curvature of the lens is much greater than the wavelength of light. So here is the Newton's rings setup. We have ray R1 that is reflected from this interface between the glass and air, and R2 from air glass. So you can see between R1 and R2 we have a path difference developing. If it's close to normal incidence, this path difference is 2t. So when we look at this point where they are going to meet, we will see some sort of interference depending on the path difference. Okay, so first consider ray R1 that is reflected from the glass-air interface. So that's ray R1 that's basically reflected from this glass-air interface. And if we go from glass to air, because the index of refraction of the glass is for the particular lens is 1.5 and air is 1, we go from high index of refraction to low index of refraction medium. That means there's going to be no phase difference, 0 degrees. But on the other hand, if I consider ray 2, which is reflected from the air glass interface, that's this interface here, because I go from low index to high index medium, this is going to cause a phase shift in the amount of 180 degrees. Okay, so this is what I have to consider when I look at the interference condition. So for constructive interference of R1 and R2, the path difference that develops between these two rays, that's going to be approximately equal to 2t. For the ray 2 will travel this distance twice when it is close to normal incidence. That's going to be 2t, the path difference. And since we already have a 180 degree phase difference, the path difference must be equal to m plus 1 over 2 lambda for this to be a constructive interference, which means the distance traveled in air, t, must be equal to 2m plus 1 lambda divided by 4. Now, which lambda is this? This is the rays traveling in the medium, which is air here. So this is going to be the wavelength in air. Okay. Now, if I look at the geometrical construction here, so I have this radius of curvature, capital R, and this is my distance I travel in the air medium, that's t. So you can see this part is going to be R, capital R minus t. So I have this right triangle. So if I look at the radius of the ring that I will be observing, because it's going to be a symmetrical situation when I look at the same distance from the center everywhere, I'm going to obtain a relationship between the radius of curvature of the lens, which is capital R, and the radius of the ring that I will observe, R, and thickness of the air film, T. From this right triangle, the hypotenuse capital R square is equal to capital R minus T square plus the radius of the Newton ring square. And the diameter of the ring that I will be measuring is 2r. That is diameter of the ring. All right. And this tells me that capital R square minus R square square root is equal to capital R minus T, where T is for constructive interference 2m plus 1 lambda divided by 4. And I know that capital R is much greater than lambda. This was given in the problem statement. The radius of curvature, capital R, is much greater than the wavelength of light. Okay, so if I square both sides, I will obtain capital R square minus R square is equal to capital R square minus 2 capital R 2m plus 1 lambda divided by 4, and then I have plus 2m plus 1 lambda divided by 4 parentheses squared. Okay, now from this equation I can pull out the radius, and the first thing I notice is that there is a cancellation here. These capital R squares will cancel, and I can obtain an expression for the radius of the Newton ring squared. So that gives me R squared is equal to capital R lambda 2m plus 1 divided by 2. Why divided by 2? Because this 2 makes this 4, 2. And then I have minus 2m plus 1 lambda divided by 4 parentheses squared. Okay, so this is going to give me in lambda 2m plus 1 divided by 4 parentheses I have 2 capital R minus 2 m plus 1 2m plus 1 lambda divided by 4. And here I recall that my capital R is much greater than the wavelength. So looking at this part here, I can see this term can be ignored because it's much less than 2 capital R. And I'm looking at the third interference, so m is a small number also. So this is going to be of the order of lambda, therefore it's going to be much less than 2r. Okay, so with that, I will have r is approximately equal to capital R lambda 2m plus 1 divided by 2. So that's going to be this term here, lambda 2m plus 1 capital R divided by 2. Now, what changes when it is filled with water? So when it is filled with water, the wavelength that I use in this expression, lambda, will be replaced by the value in water. So index of refraction goes from 1 to 1.33, which means the wavelength lambda will go from lambda 0 to lambda 0 divided by n, let's say. So lambda 0 is the wavelength in air. Or because I called it lambda already, let's say lambda in air is going to become lambda divided by the index of refraction of the water. So, if I look at the diameter 2r, it's going to be the diameter that I measure in air, 2r air, and here I have a square root, I have forgotten. So I have r depending on square root lambda. Now if lambda goes to lambda over n, so this is going to be scaling as 1 over square root n. So I'm going to have 2r air divided by square root of n, so that I will have the diameter that I measure in water equal to the diameter that I measure in air divided by square root of the index of refraction of the water. So this is going to give me the diameter in air was measured to be 0.64 millimeters. So it is 0.64 divided by 0.64 divided by square root of 1.33. So I will find the diameter of the ring in the water to be 0.555 millimeters. Okay, so let's take a look at what we did here. So we're observing these Newton's rings. So we are looking at a distance r from the center. And when we are at a distance r from the center, we have the ray 1 that is reflected from the lens air interface and ray 2 that is reflected from the air glass plate interface, interfering to give me an image. Now, if R1 is following this path, R2 is following an additional path length of 2t. So when I'm at a distance t from the glass plate, you can see that the radius of the Newton ring that I will obtain is related to the radius of curvature of the lens, as capital R square is capital R minus t square plus r square. And that path difference between ray 1 and ray 2, 2t, should be equal to n plus 1/2 lambda for constructive interference. Why? Because there is a phase shift that is occurring for ray 2 during the reflection from the air glass interface. Which interface is that? That's this interface. Okay, so 2t is m plus 1 over 2 lambda, where m is an integer. So this tells me that t is in the form 2m plus 1 lambda over 4, which I substitute into this Pythagorean theorem, and I solve for the radius of the Newton ring using this expression. And then when I do that, I also realize that capital R is much greater than lambda. This is given, so one of the terms disappear, and I obtain R, the radius of the Newton ring, to be square root of capital R lambda 2n plus 1 over 2. So I can see that the radius of the ring scales as square root of lambda. So if I change the medium from air to water, the index of refraction increases, the wavelength decreases, so lambda becomes lambda over nw, which means the diameter that I measure in air divided by square root of n, square root of the index of refraction of the water, will give me the new diameter that I will measure. So the diameter in water is diameter of air divided by a square root of the index of refraction of water, and that gives me my final answer, 0.555 millimeters.